So, yes, so here we're going to speak about I'm going to speak about the quadratic assignment problem and about what different kinds of quadratic assignment problem instances there are, and how different algorithms are going to handle solving them better or worse. And to investigate that, we use instance space analysis now. In the past, some more primitive techniques. Oh, hold on. So get rid of all these Zoom messages. Okay, here we are. Okay, so as Kate was saying, this project goes back a way. So I have here a paper which Kate wrote at Deakin in 2007. This is kind of the the germ of instance space analysis, you could say. This plot here is using self-organizing maps, right, to map out quadratic assignment problem instances. Then in 2012, there's some of the results from the principal component analysis based analysis, which I worked on at Monash in that undergraduate project, and Tim Wilson is my guest here today. Worked on evolving new instances to be easy or difficult, and now at Optima, new set of tools. Can we build on those and find out even more about the quadratic assignment problem? Okay, so for those not familiar, a brief outline of what instance space analysis involves. We have a problem space, in this case, the quadratic assignment problem space, and a set of algorithms. And we want to understand how the algorithms interact with the problem space. Where do they perform well? Where do they perform poorly? Now, if we could run every possible algorithm on every possible instance, this would be fairly easy. But we can't, of course, because there's an infinite number of algorithms, and for that matter, an infinite number of algorithms. There's an infinite number of instances, and for that matter, an infinite number of algorithms. So we have to sample the problem space and sample the algorithm space, and then try to generalize from those results. We do that by trying to select a subset of the quadratic assignment problem space, which is going to be representative of the space as a whole. So we have this subset here, and then to generalize from that, we measure features of our quadratic assignment problem instances. And hopefully, if we have instances with similar features, we can hopefully draw the conclusion that that algorithms will perform similarly on instances with similar features, if we've chosen our features well. Now, quadratic assignment problem, as Kate alluded to, is rather of the instance space analyses I've been involved with and read, this is the quadratic assignment problem is going to pose some special challenges, right? So there's going to be, so I'm going to move fairly quickly. There's going to be a fair few details. Unfortunately, a lot of those details do turn out to be important. Okay, so first, quick overview, again, for those not familiar, what is the quadratic assignment problem? In short, quadratic assignment problem consists of, given a set of facilities with desired flows between them, and given a set of locations, same number of facilities and locations, the locations have distances between them. We want to assign one facility to one location, every facility to a unique location, so that the cost is minimized. And the cost comes from multiplying the flow along each link by the distance which it's been assigned to. This kind of facility location representation is just sort of how the problem's typically thought about. In reality, the mathematics is just, takes in two arbitrary matrices and then calculates this quantity based on the permutation which sets the assignment. And so this here happens to be the optimal solution for this particular tiny instance. Now, the quadratic assignment problem is very difficult to solve as the size of the problem increases. Anything above about, I think these days it's anything above about 40 facilities and locations, unless your problem happens to be easy, is going to be intractable for an algorithm which is trying to solve the problem exactly optimally. But heuristics, which is what we're going to be focusing on here, tend to do a lot better. So just a bit of a sidelight here, which again will be useful later, about the quadratic assignment problem, the number of potential assignments, n factorial. We have n facilities, n locations, n factorial possible matchings between the two. So for any reason, for any interesting number of facilities and locations n, we cannot enumerate them all. If you could, the problem would be easy. However, there are some clever ways to still calculate things about the entire solution space. And most of these boil down to the observation that if you consider one particular flow and one particular distance, the number of times across the entire solution space that flow is assigned to that distance is a constant. And it's constant across all of the different flows and different distances. And what that means is that you're calculating the average, for instance, boils down to just a set of summations. You rearrange those summations cleverly, and you can take something which was, factorial n factorial to calculate, and you can calculate it in polynomial time instead. So the average solution value, the standard deviation of the solution value is a fair bit trickier, but you can still do it in polynomial time, and then these later quantities, trickier still, but it can be done. Most of these results are kind of known in the literature. Some of them have become known in the literature, since some things which I found out in 2012 have since been published, which is a bit unfortunate. But some of them, even if they were known, we've managed to improve the computational efficiency. I've gone from on to the power 4 to on squared, for instance. Okay, so that's a brief overview of what the quadratic assignment problem is. How are we going to choose a problem subset? Now, this is fairly classical for those who've worked with instance space analysis before, or any kind of benchmarking procedure. There's several different places you can get instances from. Quadratic assignment problem happens to have a standard library, QAPlib. There are also other published benchmark instances which haven't quite made it into QAPlib, but are still well known in the literature. Beyond that, some authors have published instance generators. They haven't bothered to publish specific benchmark instances, but they've made the generators available. And then finally, if we think those first three aren't quite sufficient, we can generate new instance generators ourselves, which in this case is going to happen both before and after the instance space analysis. Before, we can immediately see there's a hole, even without doing any analysis, that we want to fill. And afterwards, when new ideas present themselves based on our instance space analysis. So this is a brief summary of where the instances came from and their properties. I'm not going to get into too much detail here, otherwise we'd be here for hours if we went into all the details. But the really important thing to take away from this table is that if we look at the descriptions here, so the first one, real data, sure. Second through fourth, they're all based, all of these kind of categories of instances, and these categories are derived from from previous papers that were searching for a categorization. This isn't just something I've made up. These categories are based primarily on the structure of the distance matrix. Fundamentally, how people come up with instances for the quadratic assignment problem seems to be they have some clever idea for how to construct a distance matrix that'll be interesting, and then they make up a flow matrix to go along with it. And more thought's been put into the distance matrix. That's going to be important later. Okay, so those are our instances. Now, what are we going to measure about them to try to predict algorithm performance? So before we even define any features, there's a big problem to solve here, which is that you can write down a quadratic assignment problem in several different ways and have it boil down to the same thing. So one obvious example, if you take all the distances and double them, you haven't really fundamentally changed the problem much. You've just rescaled your objective. But some features some features, including some actually which have been used in previous highly cited papers, would change based on this modification of our problem data that actually makes no difference at all. So We can define a pair of similar quadratic assignment problem instances as like this. And what all this math boils down to is anything which any pair of instances which are related by adding a constant or multiplying by a positive constant or by rearrange this automorphism f of s of n boils down to, if we kind of rearrange the solution space, but all the solutions which were there are still there, and any solutions which were adjacent are still adjacent. Any combination of those operations, we're going to call a similar quadratic assignment problem instance. And well, I don't have any tables for it in these slides, but practically for the algorithms we're considering, pairs of similar quadratic assignment problem instances, the algorithms are equally good at solving. So, yes, we have a definition of what similar means, but how, what kinds of instances are similar. So like I said, you multiply your distances by a positive constant, doesn't make any difference. Multiply flows by a positive constant, doesn't make any difference. If you add a constant to, if you add 1 to all of the distances, then what that's going to do to every single cost of every possible solution is just add the sum of the flows, right? And vice versa, add 1 to all the flows, you add the sum of the distances to the cost. Again, doesn't really make much difference. And so all of these are fairly straightforward to deal with. We define a standard form which says, if any two instances are similar, we define our standard form so that they'll reduce to the same standard form. And we make some use here of those statistical quantities I've talked about earlier. So one of the properties of the standard form is that we arbitrarily say that the standard deviation among all the possible solutions to this problem, we set that to 1. We rescale our matrices so that that's the case, with the hope that that makes our solutions from one instance to another one a bit more comparable. But there's a bigger problem than everything in this list, which is that, as I alluded to earlier, the distances and the flows are interchangeable, right? Because we can think of the quadratic assignment problem as being a problem where we assign facilities to locations. We could also think of it as a problem where we assign locations to facilities, and the model's exactly the same. And if you go and open in QAPlib or anywhere else a quadratic assignment problem data file, it just gives you 2 matrices. It doesn't label one as the distance matrix, which is a problem if we want, as has been typically done in the literature, to measure features about the distance matrix or the flow matrix. In fact, if we want to measure features, even if we give up on a distance matrix and flow matrix designation, if we're applying features to the first matrix, then if we flip around the order of the 2 matrices, then those features are going to be very different, but our problem's essentially the same. Not good. So our solution to this is, not all of the instances, but a lot of the instances that have been considered do have something you could describe as a distance matrix. So we're going to try and, a flow matrix could be almost anything. A distance matrix probably is going to at least sort of look like it respects the triangle inequality. Now, given that we can just add or subtract arbitrary constants from all our distances, identifying the matrix which looks like it satisfies the distance equality, the triangle inequality, isn't as easy as it sounds. But we found a method which, if you tune the parameters correctly, for all of the instances in QAPlib where the authors said, yes, one of these is the distance matrix, our method correctly identifies that matrix. So it's about as good as we can do. So now I'm going to run through the features we're measuring. I'm not going to spend too much time here. Again, we could be hours at this. But important to remember, there are 3 distinct categories of features we're going to be dealing with. First, we have features which we measure for each of the 2 matrices independently, the distance matrix and the flow matrix we identified before. One thing to be careful of here is that our features don't necessarily mean what you would think after we apply the standard form. So if you take this example distance matrix up in the top right here, so that's just Manhattan distances. once we apply our standard form, we subtract 1 from all of these distances. Now we have some distances 0. So the distance sparsity of this top right instance is in fact going to be fairly significant, because once it's in standard form, which is where we measure the features, it has a lot of 0 distances. I'm not drawing in here distances from a location to itself, even though they do exist in a quadratic assignment problem. Don't worry about that detail. So we have features for individual matrices. We also have features of the problem as a whole, which take into account both matrices at the same time. Some of them are just a case of take the maximum value of this feature across the two matrices. Some of them are a bit more complicated, like the landscape ruggedness. So you see this example plot here. Low ruggedness means that relative to the variation across the entire solution space, the variation between adjacent solutions tends to be low. High ruggedness means it tends to be high. And again, this is something which you wouldn't think you could calculate exactly, given that you have to understand the entire solution space, which is of size n factorial. But again, those statistical measurements we talked about at the start, which we can calculate in polynomial time, kind of give us a back route into calculating this quantity exactly. However, there are some properties of the fitness landscape, the solution landscape, which we can't measure exactly. And so for those, we have some features based on random sampling, which sample, essentially the idea is you sample some solutions randomly, then you have to do some local search procedure to find nearby local minima and measure some features about those solutions and the minima that were near them. Unfortunately, this random sampling procedure does actually take a fair while. I would say it's on the same order, less, but on the same order as actually solving the problems. So for a practical algorithm selector, using these would not be ideal. But for our purposes here of just wrapping our head around the problem, we've allowed ourselves to use them. A practical algorithm selector would probably try to find a way around these. Okay, so that was our features. Now we're going to talk about the algorithms we're comparing. So we're just going to compare 2 algorithms. As we're going to see, that gives us quite enough to worry about. And the 2 algorithms we're comparing here are 2 heuristics, but considerably different character. BMA is an evolutionary algorithm. MMAS is an ant colony optimization algorithm. Both of them use some form of local search to improve the solutions they come up with. That's just a decision made by the designers. There are some important differences between how these 2 algorithms perform, which we'll get to when we see the results. We did consider this breakout local search that BMA uses to improve evolved solutions. We did consider using that as a 3rd algorithm, but it tended to perform worse than BMA. And also we're finding that including a 3rd algorithm, especially if it was only good on a very small part of the space, the instance space analysis projection still treats that algorithm as being just as important as the others. So if we want to find things out specifically about the 2 most competitive algorithms, it maybe makes more sense to just compare them head to head. So we now have these 2 algorithms, they're 2 heuristics. How are we going to compare them? Once again, this is where we end up back in difficulties. So these algorithms, like I said, they're heuristics, as opposed to, as Kate was mentioning in some previous work of ours on the knapsack problem, there we were comparing exact algorithms. You just run them, see how long they take to find the optimal solution, and then you're done. These heuristics, the situation's a lot more difficult. So we're going to solve that. Several solutions this problem exists. The one we've chosen is run each algorithm for a fixed amount of time and then record the best solution which it found, right? Now the instances have different sizes, meaning that an appropriate amount of time to solve an instance with 25 locations and facilities is going to be very different to an appropriate amount of time to solve a problem with 100 locations and facilities. We solve that by running some preliminary experiments, give the algorithms plenty of time, see at what point does their progress slow down, and then based on that, define a reasonable function mapping problem size to how long we're going to give the algorithms to solve them. And then these are heuristics, their behavior is random to some extent. And with some experimentation showed that running each algorithm 50 times gave us a pretty reliable idea of which one was better or if they were functionally performing very similarly. So these were all fairly simple problems to deal with. Like with the features, I've saved the nasty one till last. Many of our instances, we don't know what the optimal solution is. Even some of the instances in QAP-lib, the optimal solution is just not known. And the instances which we've generated with a generator, we have no real way to know about those either. And so, unfortunately, we can't really say much, without knowing the optimal solutions or really, anything much about how, what constitutes a good solution in the abstract sense to these instances. We can't really make any pronouncements about which of these instances are hard or easy. But what we can still do is compare the performance of the two algorithms and say, well, where is one of these algorithms significantly outperforming the other? But of course, the definition of significantly outperforming, that's still difficult. Now, we could potentially use the standard deviation. Remember, we set the standard deviation of the solutions in all of these problems to 1. So that's kind of consistent. We could just say that if you're 0.2, if you're consistently generating a solution 0.2 better than the other algorithm, you're significantly better. But that's a little underwhelming because that standard deviation across the entire solution space, that's taking into account a lot of really bad solutions. We're more interested in, among the plausible solutions to this problem that an algorithm might practically come up with, are we significantly better in that context? And so the way our performance criterion works here is, so for each algorithm, we find its best average solution. We ran the algorithms 50 times on each instance, 2 algorithms 50 times. We have 100 data points. From those 100 data points, all of which are plausible solutions that an algorithm might come up with, an algorithm did come up with them, we calculate the standard deviation out of those, and then use that standard deviation to calibrate, how big a distance is required between one algorithm and another before the worst algorithm can be said to be actively performing badly. Now, this method, so the best algorithm is always going to get a performance rating of 0. If the other algorithm is very close, then its performance rating will be slightly greater than 0. If it's bad, it will be, it will be quite a bit greater than 0. The threshold we've set is just one standard deviation of these 100 observations. If you're that much worse on average, then the algorithm is bad. So, because we have only 2 algorithms, we can take we can make a nice plot where we put the performance of both algorithms on a single axis. So in the middle, the performance of both algorithms is 0. And on one side means that the performance of one algorithm is increasing while the other one remains 0. And if it increases, I think I might have got this 1 and -1 the wrong way around. And if it increases beyond 1 or decreases below -1, then that's our threshold for saying the algorithm is actively bad. So an algorithm can be a little worse without being bad. All right, check the time. All right, so now we have all of the building blocks. We talked about the quadratic assignment problem, what it looks like. which particular quadratic assignment problem instances we're sampling, what features we're going to measure about them, and the algorithms and their performance, and how we're going to assess that performance. So having put all that together, we can now run our instance space analysis tools and get some results to look at from the 2D projection. And so the 2D, so for this first instance space analysis, we're choosing six features. If you go and look it up on the Matilda website or type it into MATLAB or Python, whatever, you're going to get a 2 by or an n by 2 matrix. Here, I'm a bit easier to read. To represent it as with these arrows. So if an instance has high distance sparsity, then that will tend to push it towards the bottom right of the plot, and so forth. And so here is, so here's a plot comparing the performance of both the algorithms, taking advantage of that. The system we talked about a moment ago. If we had 3 algorithms, we'd need a separate plot for all 3. But with only 2 algorithms, we can kind of get all the information on one plot. And so these triangles represent instances where one or the other of the algorithms is actively bad, and therefore the other one is much better. And the dots are instances in between this -1 to 1, where one of the algorithms is potentially a little bit better than the other, but not up to the threshold of one of them being the only good algorithm. So what we're seeing here is the ant colony optimization tends to be superior in this top left region of the space, although there's plenty of instances up there where we don't quite cross the threshold of the evolutionary algorithm being bad. And across the rest of the space, either the evolutionary algorithm is the only good algorithm, particularly on the right here, or as we see down the bottom, there's several instances where the algorithms are performing about the same. So again, ant colony, good up the top left. Evolutionary algorithm tends to be the algorithm of choice elsewhere. So one quick thing we can check is the standard QAP-lib library. How good is its coverage of this space? And we see immediately its coverage of the region where the ant colony optimization is performing particularly well. The coverage of QAP-lib in that region is very poor. So obviously there's a problem with the standard benchmark library. If you tested these 2 algorithms based on the standard benchmark library, you would come away with the impression that the evolutionary algorithm was much, much better. Whereas in reality, maybe it's the situation's a little more complicated than that. So this is from the ISA tools, we generate a support vector machines which predict where each of the algorithms will perform well and where it will perform poorly, and then the toolkit combines those 2. In this case, we have 2 algorithms, combines those 2 SVMs into an algorithm selector. And the way that the default instance space analysis tool does that is it looks for the support vector machine with the greatest precision, I think it was, but it's one of the, is a global characteristic of the support vector machine. And the support vector machine with the greatest precision gets trusted first to pick out all of the instances where it believes its algorithm will be good. And then in turn, we go through the other SVMs and they get to pick through the remainder. Now, this predictor isn't using that, because what we found using the default instance space analysis combiner of SVMs is the evolutionary algorithm was predicted to be the algorithm you should choose almost everywhere. Because if we look here, a lot of these instances, maybe the ant colony algorithm's a little worse, but it's not crossing the threshold to actually being bad, which is what the support vector machine cares about. So the BMA support vector machine was saying, yes, okay, you could potentially pick me up in the top left. And then its precision was very high because the support vector machine corresponding to BMA was getting to run up the score in this large part of the space where it's never wrong. So the way we've combined them for this, the two support vector machines for this plot, is to look at, I won't go into too much technical detail, but we're looking at locally which of the support vector machines is more confident that it's going to, the algorithm it's representing is going to get a good result. And using that technique, we have a algorithm selector which, both eyeballing it and if you actually look at its accuracy in predicting the best or a good algorithm, this predictor is better than the default instance space analysis toolkit one. So this is all looking good so far. We have this nice separation between the instances which are good for one algorithm and the instances which are good for the other. We have some holes maybe in the instance space, maybe we could fill them, but there's a bigger problem here. And to explain it, I'm going to have to go back to the projection matrix represented by these arrows. So let's actually have a look at what these features are. We have distance sparsity based only on the distance matrix. Flow matrix doesn't come into it at all. Similarity of the distance and flow distributions, okay, that's both matrices. Location similarity to nearby locations. Locations are based on the distance matrix. Distance satisfaction of triangle inequality, only the distance matrix. This alpha parameter of best fit beta distribution of the distances, only the distance matrix. Average distance to local optimum, oh, I got you this time. That's distance in the solution space. That's one of the fitness landscape features. But nevertheless, we have 4 features based only on the distance matrix. One which uses the distance and the flow matrix, and the fitness landscape feature is inherently taking advantage of both matrices. But if we look at the direction of these two features, which are taking into account the flow matrix, they seem kind of orthogonal to what's separating the performance of one algorithm from the other. Right? So our decision about which algorithms are going to perform well on these instances seems to be completely driven, or almost completely driven, by the distance matrix. The flow matrix isn't coming into it at all. But the flow matrix is fully half of the problem. As far as the mathematics is concerned, it's equally important. And so this goes back to what I said back at the very beginning about our instance subset, that people designed these instances by coming up with a clever idea for a distance matrix and then just picking a flow matrix willy-nilly to fit. That our instance, our instance subset is primarily driven by variation in the distance matrix, which raises the question, does it have to be? Can we come up with instances where their difficulty is being at least equally driven by the flow matrix? And so that's what, rather than directly trying to fill holes in this instance space, we're first going to interrogate, well, is there something fundamentally wrong with the instance subset we've chosen, that it's laying too much emphasis on one matrix and not enough on the other? So, first idea, very basic. Take instances from, or take a distance matrix from one kind of instance, take a flow matrix from a different kind of instance, merge them together into one new instance. Now, I've said, we took a distance matrix from one place, a flow matrix from another. Our selector of which one is, in our new instance, which one are we going to label as the distance matrix, might not match what they were before. But that's not a big deal. It's still a valid instance. And what we see from these instances is now, we're filling in some holes in the space, which is nice along the way, but we're now generating a bunch of instances in this top left region. Remember, that was where the ant colony algorithm was particularly good before. Now we're getting instances up here where the evolutionary algorithm is clearly strongest. So clearly there was something wrong with our projection, and which is caused by the limitations of the instance set we're working with, because we've come up with some new instances which completely contradict the conclusions we had before. But this is only half the problem, really. That we've created some new instances in the region where MMAS was good, which are good for BMA. Can we do the opposite? Can we generate instances in a region where BMA was good, which are instead good for the ant colony algorithm? And well, this is going to be a little bit difficult, right? Because when we just did something without a plan, we got almost all instances which favored the genetic algorithm. And we can't draw positive conclusions from our projection. We know our projection's lying to us. We have to think about what are the features we're measuring not telling us about the problem. It's kind of an inverse to how drawing conclusions from instance space analysis usually works. So what are our features not telling us? So, and to think about that, we're going to focus in on some particular instances which have what I'm going to call jackpot solutions, where there's a few really, really good solutions compared with the rest of the solution space is not very good. And some of these instances with jackpot solutions favor one algorithm, some of them favor the other algorithm. So we have some representation from both. And they tend to be very polarizing. They're either very good for one algorithm or very good for the other one relatively. And sat down to think about it for a while. There's a fair bit of thought. But the conclusion come to is that the ant colony algorithm is what it particularly wants to do is it finds a component of a good solution, like a good component of a good solution. And then it tries to build on. Which, if there's only one jackpot solution, is great. You found a good component of that one solution, you're going to keep pursuing it, you'll find the one great solution. If when you find a component, when you find a good component, it can boil down to many good solutions, then you've narrowed yourself down to good solutions, but you still have some flexibility. But on the other hand, if there are a bunch of good solutions, but perhaps not all equally good, and so we have a bunch of solutions, not all equally good, like a bunch of good solutions, but not all equally good, rather. And they're very far apart, so that if we find a good component of a solution, it only corresponds to one of those jackpots. Then when we find that small bit, we're then committed to that one jackpot, even though there might be a better jackpot somewhere else. And if the evolutionary algorithm's consistently finding that other better jackpot, then the ant colony algorithm is going to look considerably worse according to our performance metric. So in particular, some instances where the genetic algorithm was particularly doing a lot better than the ant colony algorithm look like this, but with more locations and facilities. We have a grid structure in both the distances and the facilities. And so we think about this. As this problem stands, there's 4 good solutions, corresponding to just mapping these directly and to vertical and horizontal flipping. And if the ant colony algorithm figures out facility A and facility B should be next to one another, and it puts facility A in the top left, facility B in the top middle, then we're then committed to that one of the 4 solutions. Okay, that's not too terrible. Sometimes, not necessarily commonly, but enough to drag down the average performance quite a bit. The ant colony algorithm might decide to put A in the top left and then B in the bottom left. At which point, that looks good kind of locally, but the rest of the problem's not going to work out. So what can we do to keep this distance matrix so that we're still in the part of our space where we were predicting the genetic algorithm would be good, but can we modify our flows so that it now favors the ant colony algorithm? And so something looking like this, sort of, seems to work, where we, instead of having one big monolithic group of facilities, we split it up into several smaller, there's still groups of facilities, but they're smaller, so that now if we put facility A in the top left and facility D in the middle top, there would still be quite a few potentially good solutions available. For this, for this new problem, the ant colony algorithm, the ant colony optimization, assuming that the thing it's latched onto at the start isn't completely daft, it still has, it's not only it hasn't locked itself out of all the jackpot solutions, and it may still have several to choose from. And it turns out that instances looking like this, indeed, a lot of them tend to favor the ant colony algorithm, even though they're all the way over here, which is way away from where all of our good instances for the ant colony algorithm were before. You see there's a few instances still in here where the genetic algorithm is still strong. That kind of depends on how you set the parameters for these instances. Won't get too deep into that. But so now we have, we've kind of completely blown a hole in our original instance space. We found instances on the left which were not, which performed completely different to the other instances which started on the left. We've now created instances on the right, where the algorithms perform completely different to the existing instances on the right. So having done that, let's run our instance space analysis again. This time we have 7 features. And this is what our instance space looks like now. Unfortunately, much messier, but we're no longer lying to ourselves that we know something that's actually untrue, which the way I see it's an improvement, right? And kind of the idea which, and this perhaps shouldn't be surprising, because the idea which kind of drove those new instances which we added, particularly the ones which favor the ant colony algorithm, those ideas aren't reflected in our current feature set. Unfortunately, it's not really obvious how to measure them, without taking an extreme amount of time. So, this isn't a wholly happy ending, right? We haven't quite solved all the problems, but we've got to the point where the paper is extremely long already, and we have to submit something sometime. We've come up with several new developments, several new instances, blown a hole in many existing ideas. It's time to tell everybody we've blown a hole in these ideas so that, so that us and other people in the future can think about it in the light of these holes we've blown. One particular thing I'm going to point out about these features is that we now have 2 flow features, the normalized flow mean and the flow dominance, 3 distance features, normalized distance mean, distance skewness, distance sparsity, and then the Gilmore-Lawler bound and the escape probability are, they take into account both matrices. But the two flow features are just about collinear, and the distance features, are kind of, very loosely speaking, perpendicular. So what this instance space is now boiling down to, we have the properties of the distance matrix in one direction and the properties of the flow matrix in the other direction, which is kind of where these lines you can see come from. Those are instances where the flow matrix is changing, but the distance matrix isn't really. All right, so one last little bit. Okay, one last little bit. Evolving new instances. Turns out, as Tim could tell you, if you try to evolve instances directly based on the performance of algorithms, very slow. You have to work with small instances, because using the actual performance of an algorithm as a fitness function is a very slow fitness function, right? So here we're trying to evolve to fit points in the feature space. Still kind of slow on account of the fitness landscape features I was talking about, but it's manageable. Next problem, if you just directly evolve the values in the 2 matrices, certainly every time I've tried it, there's a definite tendency for the matrices to just do something degenerate. All the values go to 0 or something, even if that's not anywhere close to the target point. So, as you might recognize from the knapsack instance space analysis, if you've heard me talk about that at some point, we're, instead of directly evolving the problem data, we're going to evolve the parameters of a generator to try to generate new instances. And we're going to lock it down even more. We're going to set the distance matrix to be constant and try to evolve parameters for a flow generator to try and generate instances with the desired properties. And as you'd expect, most of these instances are going to turn out to be along that line based on where the two flow features were. There are these anomalous instances out here. That goes back to what I said before. Just because we generated what we thought was a distance matrix in a flow matrix doesn't mean our classifier is going to agree with us. These instances up here are what happens when that definition flips around. And so all the features which we were applying to one matrix, in theory, we're now applying to the other. All right. So like I said, not a 100% happy story, but we've made some important developments, is the short version. So our contributions are, we think we understand the quadratic assignment problem much better than the literature has previously understood it. Some of those properties, like just adding one to everything in a matrix, is kind of obvious. People knew that didn't really make a difference, but they hadn't quite applied that knowledge to how they defined their features. So we've laid out a method for doing that. And in particular, the identifying which matrix is the distance matrix, that took a fair bit of work. I won't go through the entire list, but we've created new instances, which, as we saw, our original instance set was outright lying to us about the properties of the quadratic assignment problem. Our new set of instances, well, we're not getting such a clear message out of it, but at least we think it's not lying to us in the same way. We've learned some more about how, the comparative properties of ant colony algorithms and evolutionary algorithms. And we've proposed this method for evolving quadratic assignment problem instances based on evolving a generator for their flow matrix. If you want someone wanting to extend that, you could evolve the flow matrix for a fixed distance matrix, then hold the flow matrix constant, evolve the distance matrix, and keep iterating that. Evolving them both at the same time seems very difficult. For the you kind of pulling one way and then pulling the other. There's no unified idea. Trying to evolve one matrix at a time and iterating seems the more productive approach. And so I've kind of touched on some of these ideas for the future already. The one I'm going to focus on, though, has got to do with these plots down the bottom. So the plot on the left is the support vector machine, which the support vector machine selected for the first instance space I put up earlier. And it's got different colors on it for a reason which will be apparent in a moment. On the right here is a plot from a paper which Cadence and colleagues at Monash published 10 years ago on the graph coloring problem. And so the cyan instances on both of these correspond to an evolutionary algorithm. The red instances correspond to an ant colony algorithm. Here we have, in the graph coloring problem, they're considering a bunch of other algorithms, but the kind of the most critical part of the space where it's important to get your algorithm selection right, because there's only one good algorithm, tended to be this upper right region. And we kind of see a similar sort of pattern where on a lot of the relevant part of the space, the genetic algorithm's better, but there's this corner where the ant colony algorithm has an edge. And in the graph coloring problem, that little corner seems to correspond to instances where your graph, and therefore your problem, it's connected, but not too connected. And then there's, perhaps I don't know enough about the graph coloring problem to take the idea a lot further than that at present, but there's a suspicious similarity between the properties of this connected but not too connected idea, and the ideas we use to create those new ant colony favoring algorithms on the right-hand side of this space. So, something for us or someone else to think about in the future, some kind of comparison of algorithms, which is in some sense independent of the problem space you're working on. Is there something we can say about the algorithms in general? All right, I think that wraps everything up. A few references here. Thank you all for coming and listening.